All right, I want to talk a little bit about failure under complex stress conditions. When you took your materials class in the laboratory, you did a uniaxial tension test. And from that test, you got a stress strain curve. And we've simplified it here, or I've shown just a simplified bilinear stress strain curve. And we're going to call the yield point sigma yp. Now, the question becomes that, okay, so this guy named Tresca was famous for that. He tested steel to failure under different stress conditions. And he tried to answer the question of how multiple directions of stress would affect failure. And in the end, he developed something called the Tresca Hexagon, which is what we're getting to here. In other words, when you do the uniaxial tension, that gives us a very simple stress strain curve. But what if we take, and instead of just putting on uniaxial tension, we actually put on stresses in both directions, for instance, both the vertical and horizontal directions. So in other words, let's remember how you did this test. The uniaxial tension test was what? You simply put it in the machine and then you kept on increasing the tension a little bit at a time until eventually you couldn't increase it anymore because the material had failed. So in other words, I kept on increasing this stress until failure occurred. But if envision this, instead of doing that, what if we put on, for instance, 10 kips per square inch in the vertical direction and then kept on increasing the horizontal stress until failure? Would I get a different result? In other words, would I end up with this same sigma yp? That's the question that Tresca wanted to answer. And so he tested steel under a lot of different conditions. And his end conclusion was this hexagon. And the way that it worked, what he found was the following. In other words, he tested, he ran this sort of test over and over and over again under different situations. And his end result plots were these. He plotted sigma 1 on the x-axis and sigma 3 on the y-axis. And given the and he figured out, or basically he was able to do the test and figured out whether or not you got failure or you did not get failure. So what I've shown here are the results of numerous tests of his. For instance, each point on this plot represents one test. And anything that was in the hexagon indicated that there was no failure. And he found that if he ever loaded something that was outside the hexagon, that he got failure. And so we can use this hexagon to help us predict whether or not a complex stress condition would create failure in our material, steel in particular, the heated steel. So we're only talking about steel right now. Interestingly enough, if we do a different material, we get completely different results. So we're talking about steel. Now, to create this hexagon, it's very straightforward. You're going to need to create this. I take my sigma yp. That sigma yp comes from where? That comes from the uniaxial tension test. So what he did was, he used the uniaxial tension test because it's very simple to run, and you can get that value. Then you can use it to create the hexagon. So if you look at this hexagon, it's straightforward. I have sigma yp here, sigma yp here, sigma yp here, sigma yp here, and then to create the hexagon, you just put a square in quadrant 1, a square basically in quadrant 3, and then connect the others like that. The only mistake that people ever make with this pretty much is that they'll draw the hexagon in the wrong direction. Don't do that. The hexagon should look like this, sort of pointing upward to the right. Other researchers have done stuff like this. For instance, von Mises, he did steel also, and he decided that the hexagon wasn't quite right. He thought that it really was an ellipse. Okay, so this is the sort of thing that people can argue about for long periods of time. For us, we're not going to worry about the ellipse. They're almost identical, so we're going to stick with the hexagon. And you can do different materials. Okay, so concrete would look something like this, for instance. You could make a whole career out of this field, by the way, pretty much, looking at materials and how they fail and, trying to predict failure in various ways. Now, why does this make sense for concrete? Because concrete does not take much tension. It takes a lot of compression. So when I'm over in here in quadrant 1, this is tension. So I have very little for concrete there. Over here in this quadrant, we are showing compression, and it takes got a lot of compressive capacity for concrete. So each material will have a different shape, different ways it's represented, and I'll show you one more. Soils are typically represented by this, which is our Moore plot, where I have sigma tau. And you draw the Moore circle, and if the Moore circle is below the failure, what's called the failure envelope, that's given by an angle of phi prime. If the Moore circle falls below that envelope, then there's no failure. If the Moore circle falls, if you end up drawing a Moore circle for your stress condition that's up like that, then you get failure. So, like I say, many different materials have many different types of representation for failure. But we're going to focus on the Tresca hexagon. Okay, so the way to work these problems is pretty straightforward. The first thing we have to do is draw the Moore circle. So I'm not going to go into detail here, but let's just say that we have this stress configuration. And our goal is to decide, does this cause failure? I'm going to give you that sigma yp is 6 kilopascals. And that the Tresca hexagon works for this material, and the question is, does failure occur due to that? Now notice that My sigma YP is 6 kilopascals, and none of these stresses, that's 3, that's 2, that's 5, none of these stresses are greater than 6 kilopascals. So, in other words, we haven't applied, in a sense, we haven't applied really large stresses to this. But we're going to determine whether or not this causes failure. So you can do this at home. We draw the circle, -5, 2 on the horizontal plane, 3, -2 on the vertical plane. We get all of the radius, etc. But what we're interested in is the sigma 1, which is the center plus the radius, sigma 3, the center minus the radius. That's what we want to get out of this, is the sigma 1 and sigma 3. Okay, so our sigma 1, sigma 1 is 3.47, sigma 3 is -5.47. And let me just clean that up for a second for you. So what we're going to do is we're going to plot these two values on the Tresca hexagon. So we have to make the Tresca hexagon first. How do we make the Tresca hexagon? We do it using the sigma YP value given. The sigma YP value was given to be 6 kilopascals. And so notice, again, neither sigma 1 nor sigma 3 is greater than 6. So at this point, we're sort of having, we have to do the problem, but at this point, we may think that there would be no failure because everything is less than 6. So what we're going to do is we're going to plot that value on our hexagon. So how do we create the hexagon? Well, it's simple. I have 6. I put down 6, 6, -6, -6, 6 everywhere. Quite straightforward. Then I make a square in quadrant 1, a square in quadrant 3, and connect the two there. So my goal is to figure out whether or not my point, there's my point there, sigma 1 and sigma 3. So remember, this is sigma 1, this is sigma 3. I put those 2 points, I put a point with those coordinates onto my plot. Okay, so that's easy enough. The value of sigma 1 is 3.47. Well, so I have to plot it sort of to scale in a way. But so I come in here, here's 3.47 on my plot. It's less than 6. And then I have to plot -5.47. So now I'm going to go down 5.47, and where am I? I end up outside the hexagon. So it fails. It fails because it is outside the hexagon. So that's in a sense, that's the value of this method. At every step that we worked this problem, it seemed like it would not fail, but indeed this one actually does fail because it falls outside the hexagon. Now, the easiest way to figure out whether it's inside or outside the hexagon is that I know this is I was given this is 3.47. I know that this is 6. So I can create a little triangle here, and I get this is 6 minus 3.47, which is 2.53, and I know it's a 45-degree angle, so that this distance right here is also 2.53. Since that's 2.53 and my value of sigma 3 is -5.47, then I know that I'm outside the hexagon. That's the easiest way to figure out whether or not it's in or not. Okay, so here's a simple problem. Sigma YP is 50 kilopascals. Sigma 1 is 32. Sigma 3 is negative 12. The question is, does it fail? So why don't you pause the video right now and work this problem. In this one, you don't even have to draw the Morse circle. Okay, I'm going to assume that you have worked the problem, and the answer looks like this. We create our hexagon. We got the 50, 50, 50, 50. We draw the hexagon. Square in quadrant 1, square in quadrant 3. Connect these. There's my hexagon. And now I simply plot the sigma 1 is 32. So I come over here, 32. Sigma 3 is negative 12. I go down 12. And what do I see? I'm still in the hexagon, so it does not fail. How do I know I'm still in the hexagon? Because when I come over here to 32, that means this leg of that little triangle, this little right triangle here, that leg of that triangle is 50 minus 32, which is 18. And since I'm only going down 12, I'm finding, that I'm still within the hexagon. So no failure. Point is inside the hexagon, no failure. Okay, I'm going to stop there.